Talking about today is interdomain measurement, analysis, and control, improving connectivity at your borders, with whom, where, at what speed, how to improve your interconnections with other people. What we're not talking about today is MPLS, diffserv, RSVP, CRLDP, and all sorts of other acronyms with a bunch of capital letters that have become associated with traffic engineering. Traffic engineering is clearly a very, very big subject, and in the next 90 minutes we will cover a very, very small portion of it, but hopefully we'll cover it reasonably well. Goals for the afternoon, methods and concepts on how to improve interdomain connectivity, and depending on who you are, improve will have different meanings. If you're a Tier 1 ISP, improve might mean catching people defaulting traffic at your borders onto you for routes you didn't announce. If you're a small ISP, it might mean finding the right people to peer with or to buy transit from or to get settlement-based peering from that you get the most bang for your buck. Another goal, finding ways to reduce impact of failure in peer transit networks. You know, what things can you do in order to keep your neighbor networks from having trouble reaching you? And some of the stuff we're going to do has some operational complexity, so keep that in mind. And if you're squeamish about such things, you know, put on your glasses. Presentation outline. We're going to talk about defining goals for interdomain TE. We're going to talk about how to measure to get data that will answer those goals and those problem statements. We're going to apply data to those goals. We're going to talk about eliciting control and redefining your goals once you've measured and gotten some quantitative data. We're going to talk about some conceptual examples, some people who are doing this stuff, some sort of live network examples, and in the end, hopefully there will be some questions, but not just a ton. So interdomain traffic engineering goals definition, a problem statement. You can measure a lot of data. What you need to be able to do is measure data that answers questions that you have and need to answer. And there's a bit of a format to doing this. You define a goal, you measure information that applies to your goal, you analyze it, you refine your goals, because often you'll find that what you thought was the right answer qualitatively ended up not being the right answer quantitatively. And then you elicit some action to improve your network, hopefully. So step one, defining goals. What is it you need to accomplish? Examples of some goals. You know, I need to offload my NSFNet peering links outbound because they're congested. NSFNet seemed like a nice politically correct word to use at that spot in the sentence. Obviously, no one has that problem. Another goal, I need to expand my interdomain peering links klufully, right? I'm ready to expand my network. I'm ready to grow my interdomain links. Who do I go connect to, and where, and at what speed, and why? Don't just go to the people who seem like the right people because that's where everyone else connects. That's an expensive way to do business. And a third goal, you know, hey, I need to find some people. I need to identify some sales opportunities. Seems like a strange thing to talk about in a traffic engineering discussion, but, you know, when it comes right down to it, we're all here to put products on the market. Once you've defined a goal, don't be afraid to adjust your assumptions once you've started measuring. You know, just what you plan to do and what you end up doing may change substantially, and that's okay. Clue about doing all this stuff should increase as valid network data becomes available and consulted. And I just can't stress this enough. There's just a ton of people out there who go through all the trouble of measuring and collecting data and never use it. And they've just created a truckload of work for themselves that, you know, doesn't help and actually probably hurts them quite a bit because they don't use it. What sort of data should I collect? For the purposes of what we're doing and what we're trying to do, we need flow export data or some generic traffic accounting information. We need BGP routing data. We can use active measurement data, ping, traceroute going out and measuring the product of what you're offering, measuring through your network, and some amount of SNMP niceties to get nice titles for things. There's some public tools available for this, CFlowD, Zebra, Ping, Traceroute, Scotty, all number of things. There are some commercial products available that do this sort of stuff as well. And so once you've defined a goal, and you know we can choose any goal we want, you need to go measure data that will help you solve that problem. If you don't have a problem statement, you're just going to end up with a ton of data that you don't know how to use in the right way. So, you know, interdomain TE measurement or getting good problem goal specific data. Can everybody hear me? The person in the back is supposed to wave their hand and say, yes, I can hear you. So the assumed network model, there's just a zillion of them, but the one that seems to be sort of prevalent and the one that we worked with the most is the hierarchical network model. Here, your ingress and egress network services are separated from your transit services. It works in others, but this is what we're going to focus on. So here's a nice little picture that I drew. You have your core network services, and the access to those is relegated by core routers, and the access into your transport service or your transit service is by edge routers, whether they be peer routers, gateway routers, web hosting routers, customer aggregation routers, whatever. And your interdomain links or your customer links are off of the edge. That model works really well for measurement and analysis and the sort of things we want to do. We'll talk about a couple of other models. Actually, we'll talk about another model, which is much harder to work with. So types of data to measure, again, routing data. Our focus here is BGP, and I suppose if someone here has the need to use IDRP or, heaven forbid, EGP, you could do the same general sort of thing with it, but obviously, BGP4 is our focus here. Traffic data, we're using NetFlow, Flow Export v5 here. Again, any sort of traffic accounting information is helpful, whether it be TCP dump or, whatever you want to use, as long as you can get some amount of traffic load information. And then active measurement and performance data, ping, traceroute, one-way delay, jitter, all the things that are statements about the quality of the product of your services as opposed to the devices. Routing data. Routers do this reasonably well. I mean, it's the core competency by design of what a router is. Routers should route, and if they don't, you should probably get a different kind of router. Different data sets are available for measurement, IBGP, route reflection, eBGP. iBGP works really well when your problem statement is, I want to measure things outbound. I want to see exit off of my network. And when you're measuring flow data and routing data from the same device and your question is outbound, iBGP is definitely the way to go. Route reflection, another way to go. If you're trying to answer an inbound question, obviously the destination address coming into your network is going to map to a route. iBGP won't communicate that information to you. You have to use route reflection to cleanly get internal routes from your device. Choose the right one to measure based on your needs and goals. So, same general picture. If I'm trying to answer this question of traffic coming in from AS3 to my peer box 2, in order for me to see what routes and what IS paths traffic maps to across my core network, I need to use route reflection. Pretty basic BGP stuff. If I'm answering the reverse question of traffic coming from my core network services into peer 2 over the thick links going out to these ASs, those are external links, and as long as they've been marked active, my BGP collector will get those routes, and all I need is standard iBGP, because those routes are announced to me that way. Said in a longer sentence, when your goal is outbound characterization and your measurement point is the exit point for traffic, iBGP is the person you want to work with. I honestly thought that this was funny when I wrote it. Protocols hate being anthropomorphized. I really thought that was funny a couple of weeks ago. I appreciate your sympathy laugh. When your goal is inbound characterization and your measurement point is the entry point for traffic, route reflection must be used. Same picture, same idea. When you're coming in and your measurement point is peer 2, if you're looking at traffic coming in, you need to know about internal routes. That means you need route reflection. If you're looking outbound, you're looking at external routes. That means iBGP will suffice. iBGP, N by iBGP is a lot easier to do than N by route reflection, just by number of paths. Just slightly off topic, but it was a good place to mention this, the concept of full mesh BGP monitoring and the value of it. By full mesh, I mean, hey, I have a whole bunch of blue boxes, and they're all sending iBGP routes to the collector. You get a full view of what your domain is doing. You can track routes historically. You can go back and look for historical problems. You can do policy benchmarking, say, hey, I want to know when something bad has happened. Tell me. I want to know when I hear default from the wrong place. I want to know if I hear default at all. I want to know if I'm hearing, UNets routes through cable and wireless, et cetera, et cetera. Tracking med selection issues, that's a really good way to do that. But just bottom line, identifying disasters the first time cluefully. There's just so many people out there who have really bad routing mess-ups, and they just, they sort of wait for it to happen again to see if they can catch it in the act, and it hurts everybody. So it's a global table. Please, do a little bit of measurement and try and head things off at the pass. A little off topic, but I actually felt like it was sort of important to mention. Again, the full mesh picture. That one was easy to draw. Traffic accounting data. Once you have routing information, you need traffic accounting information. You could call it flow export, you could call it net flow, you could call it C-flow. I call it a major pain in my ass. You could also use S-flow, you could use, any sort of traffic accounting information. We used flow export because we were working with Cisco's and Junipers. The quick skinny on flow is basically packet and byte counters per unique set of traffic attributes, source IP, dest IP, source port, dest port, etc. It's measured from strategic routers per input interface currently. Which interfaces depends on your defined goals and needs, and we'll get a little bit more into that in a second. And there's a lot of historical complaints about flow export, and believe me, I understand it, but it really has come quite a long way in the last couple of years. It is not, it is not your grandfather's flow export technology. It works a lot better than it did in '99. So if you heard from someone once upon a time, gosh, NetFlow can't do that, that's bad, things have changed a little bit over time. Collecting flow export information as per your problem statement. If I'm doing inbound measurement, all I need to do is collect inbound on a single interface for each AS I'm concerned about. If I want to find out the characteristics of traffic coming in from AS3, all I need to do is do flow export inbound on the AS3's link and export that off. That'll answer that question. That's really easy to do. Similarly, in the hierarchical network model, if you want to answer the outbound question, it's pretty easy to do too, because there's only 2 links that can contribute to external load off of peer 2. And in any sane network, your core network services will never transit your edge box. So any traffic that's coming in those 2 interfaces is destined either for that router or for one of the exit points off that router. So in this model, IBGP and a low number of interfaces will give you all the information you need. We'll get to that. We can talk later about overlapping problem statements. That's a different story. This is an example of a non-hierarchical network, obviously. ANS back in the day was sort of an example of this, where your core services and your edge services come off of the same box. Your peering links and your transit links are on the same router, and that can cause some operational complexity because you don't know necessarily that traffic coming in one backbone link is going off the box. It may transit through to another core box. And if you're measuring on more than one core box, that means you have the opportunity to double count flows. If traffic comes in, I wish I had one of those laser pointers, but if traffic comes in one core box that you're measuring on that link, because that has the opportunity to contribute to one of your external links, and traffic is, you don't know what traffic is staying on that box or going off net there and what traffic is staying on net. If you're measuring at the next router, you have the opportunity to count the same flow on 2 interfaces, and that can skew your data. So that's harder. Said again, since flow export data is inbound only, all potential feeder links in a non-hierarchical mixed services device have to be accounted for in order to catch all outbound traffic, right? In order to know what's going on in the AS2 link, I have to measure on all of the core interfaces, assuming that none of the other ASs off that are getting transit from me. One issue is how do you know what data is coming in core link 4 or core link X is bound for the local external link, and route reflection is bad here because you can double count. If you're doing route reflection from core box in red and the one below it, you're going to get the flow applied to an AS path on box 1, then you're going to get the flow applied to the same AS path on box 2. And that means you've double counted, and that you don't want to do all this only to see your numbers inflated by 2. So and the problem only gets exacerbated by complex policy. If you have BGP policy on your network where you have different policies per box, you don't have global policy, that only makes this problem worse. Words or less on flow data. Micromanagement of networks based on flow data is bad. If you take every single flow and you try and make network decisions, macro-level decisions based on micro flows, you will never finish. It will create a terrible hysteresis on your network, and it will be a ton of work. It's just a losing proposition to try and engineer your network based on individual flows. Macro management of networks based on flows is good. Looking at long-term trends, looking at long-term information, and aggregating data so that you can see the 3 and 6 and 9 and 12 month trends in your network, that is a winning proposition. It's a lot less work, and the value to you is much, much higher. So some operational challenges with flow export data and doing this stuff. Gilb's law, which is a good thing to preface, is anything can be measured in a way that is superior to not measuring it at all, which I think is absolutely true. So some operational challenges, access lists and data export in the great beast. The Cisco 12000 router can do a whole bunch of different things, but it can only do one of the great many things. And sampled net flow on the GSR is usually distributed on the line cards, right? You've got a fabric on the box, and it all goes around the GRP. But if you have any kind of access list, export access list, outbound access list on any interface, flow export won't work on any interface. And this little slide shows it. If you have access lists configured on a router, sampled net flow won't work, and a lot of people have a lot of access lists running. If you have sampled net flow running, I don't even know what PERC is, but it won't work. And that is greater than IP coloring, which is greater than BGP policy accounting, which is greater than frame relay traffic policing, which is not frame relay traffic shaping, apparently. And I guess some of this changed in 12.0.18s, but a lot of people are running a lot of old code. So just be aware of the fact that access lists can seriously kill what you're trying to do with sampled net flow. Just being vendor neutral. Some releases of Genos have bugs where it can't export data on all the interfaces you configure on it. Look up PR20159 if you think you might be subject to that. I've seen it in 5.1R1, but not in 4.4, so whatever version of code you're running, check it out. On high-speed interfaces, the best you can realistically sample is some ratio less or greater than 1-to-1. When you get up to high-speed interfaces, OC48, OC192, the idea of accounting every packet that comes in starts to interfere with the concept of forwarding it. And quite frankly, forwarding has to take precedence over accounting because accounting a whole bunch of packets that never get forwarded doesn't help you, right? So if you need to count bytes, this is going to introduce errors. If you're trying to do something like a billing system, if you're trying to do something that is packet and byte sensitive, this is going to be a problem for you. But if you're trying to do traffic engineering, if you're trying to do capacity planning or congestion mitigation, it's okay. People really seem to fear sampling, but as long as you're not bit sensitive to it, it's okay. What you need to do is basically compare samples and make sure that the samples are normalized. If you have a 7500, 7500 doesn't do sampling. It does one-for-one packet analysis. The GSR, I'm fairly certain you can't even configure one-for-one. So if you have some number of 7500s doing flow and some number of GSRs doing flow, you need to combine the data together in order to make it normalized so it can be compared to each other, right? Just like multiplying the denominator and fraction so you can compare the numerator. If you come away with nothing else in this conversation than this, I guess it's not a conversation unless someone talks. But normalizing the data does not mean multiplying by the sample interval. The distribution of packets is not such that you can say, hey, I'm doing 1 in 100, so in order to get the real number, I'm just going to multiply all my values by 100. It just doesn't work that way. And if anyone wants to talk about it some more, I can draw some pictures later. But it just doesn't work that way. But one way that you can normalize traffic that seems to work reasonably well as long as you're not bit and byte sensitive is to take the load and the speed of your interface and take comparable values off an interface. So let's say I had 10 AS paths across an interface and each of them represented 10% of the interface load. If you take the actual interface load that you get via SNMP and take 10% of that, you can normalize your data to say, well, I know what traffic actually was on that interface, and I know relative to each other on that interface what traffic was for each AS path. I can divide that in by percentage, right? That seems to be a reasonable way to do long-term planning and normalizing flow statistics. There's some non-trivial lack of current research on statistical validity and flow data based on samples. Casey and some of her friends did a nice paper in 1993 that talked about sampling validity in the ANSNet network, but that was a long time ago, and it actually predates substantial HTTP traffic on backbones. So, I mean, basically, we have very large, very high-capacity core links. We have very large, very high-capacity peering links. We have customer links, and all of them are going to have different traffic characteristics. So all of them are going to have different traffic granularities. and knowing what a valid statistical sampling rate on each one of those types of links would be really, really valuable. And if anyone has some copious spare time, please go do that. At any rate, so the question of, well, what's a valid sampling rate? That's a really good question. And it would be really good if some people started sitting down to work on that. Or if they already are, that's great. So I, again, tried to be funny. So we talked about Gilb's law, and I made up the Gilb-Whetman construct, and that is the total PETA factor experienced through the process of network measurement is far less than the total PETA factor experienced through planning and engineering a network without network measurements. Tough, clueful statements and easy, clueless statements. I'll take the tough, clueful statements anytime. And PETA, I don't know if you guys have ever heard this, pain in the ass. And for those of you without customers may not be familiar with it, but anyway, I find this to be very, very true. Performance data, active measurement, round trip, one-way, ping, trace route, all the things that you put a probe out and measure through your network to verify the performance of your entire network. MRTG and link utilization, were things saturated? You know, are my links approaching saturation? Really important stuff, but sadly not part of our examples as we ran out of time because we had to do our day jobs.
Josh, can you talk into this? It's hard to hear you in the back.
Oh, really?
Yeah.
That guy can hear me. Sure.
Okay, thank you.
You're okay. Is this better?
It's on, right? It's on yet.
Oh. How about now? How about now? I can try and yell. Hello? Is this thing on? I'll just yell, or I'll try to yell. If anybody's having trouble hearing me, please give a yell and I'll yell louder. Performance data is really important for this stuff, but we just didn't have time to get to it, so my apologies. But, you know, it really helps in goal selection. It really helps you identify problems, and it really helps in goal reselection, you know. And bottom line is, you know, you use this stuff to figure out, am I making things better or worse? You know, I've brought up new peering, I've moved traffic around, I've done this or that. You know, quantitatively, I'm measuring my network. Have I made things better? If you have, then you're winning. If you haven't, then you're not, obviously. Applying data to your goals. Once you've defined a goal statement, once you know your problem, and once you've started measuring, and once you've started getting good data, at some point you're going to have to glue those together, right? How do I use my data to solve my problem? And focusing on what we're doing here, we're taking traffic accounting data, and we're applying it to routing attributes and routes, right? How much load is representative per AS path, BGP next hop, community list, whatever it is that you need to do. Our focus here is on traffic statistics, byte and packet rates per AS path. That's what allows us to do the how do we find people to connect with and how do we optimize our interdomain connectivity. Traffic data tables for AS paths. We take traffic load per AS path. We get every individual flow. We take the destination address and we do a route lookup in real time, and we find the AS path attribute for that, and we apply the packet and byte counters to that AS path. So what that gives me is a bunch of AS path load values, which I can overlay on top of each other to make a tree structure. And once I've done that, I can see that all the traffic that's terminating in an AS, all the traffic that's going through an AS, and you know the product of the two. So if I have some AS path 101 that has X bits per second, some AS path 101, 1234, which has Y bits per second, and 101, 1234, 9995, which has Z bits per second, I can overlay those on top of each other and see that the traffic syncing to 101 is X, the traffic transiting 101 is Y plus Z, and the total traffic aggregation that's going to or through that AS is X plus Y plus Z. And I can do this for every branch and every structure of the tree. So this addresses the middle mile ASs instead of the traditional first neighbor or edge destination AS, right? All the middle ASs in the path I can now see, so I can see the full set of relationships instead of just how people sync out to the destinations. Because when I'm a large ISP or even a small ISP, I'm not looking necessarily, when my goal is interdomain expansion, I don't necessarily care about the syncs. What I care about is the aggregation points. Where do I get the biggest bang for my buck? So once again, it allows to and through values instead of just two values. So flow export, v5, you get all these individual flow records, and you've got all this routing information. But like I said before, micromanaging networks based on flow data and routing data, well, not necessarily routing data, but flow data is very, very bad. So you need to aggregate data over time, and anyone who's ever used cFlowD is probably familiar with this concept. When you aggregate data over time frames, you want long-term. Now, long-term may be a day for you, because maybe you made a change and you're looking to see what the result is. It may be 3 months, because... Hi, how you doing? Okay, so you can do long-term averages, 3 months. I want to know next quarter who should I go after for peering, or who should I go after to buy capacity from, if that's what you need to do. Or short-term benchmarks, right? And by short-term I mean sort of long-term, because micromanaging networks via flows is bad. Data aggregation via interfaces. Wow, that's really loud. Aggregating across the set of interfaces that represent your problem statement, and this is something that Tracy mentioned earlier. It may be one interface. I may want to look at the or the traffic load in from ASX, right? Or maybe I want to aggregate all the interfaces on a router together because my router serves a given function, and I want to see what traffic is going through that router. Maybe I want to aggregate every interface I'm measuring in the entire domain, because what I really want to know is, given all the traffic I have for all the places that I'm measuring, where is my best opportunity, for expansion? And what's most common, I think, is to do N of M interfaces or M of N, whatever, where you're taking 3 of 7 links off of a router and aggregating those together, because those 3 links answer the question that you're trying to answer. They apply to your problem statement. So what do we do with all this? Once you've measured all this information, once you've got it all aggregated and you've got some amount of traffic and some amount of traffic engineering information, what does one go do? And with that, I will hand off to my good friend Joe. Right. I forget that.
Yeah. Is that good? Yes, working? Good. Everybody hear me okay? Okay. So the very second slide we had called me a token Canadian, and I may not sound like a Canadian, and that's because I'm in disguise. So, we have some assumptions about the routing architecture. The routes to our external networks are in BGP. The routes, IGB basically tells us how to find the next hop for the routes that we have in BGP. We select exit points for traffic based on BGP path selection, and that's an assumption that I think is fairly reasonable. If your network differs very substantially from that, then you have other problems to solve before you start measuring things. So, basically, I'm trying to talk about a little toolbox here of what we can do to change things. If we made some measurements and we decided that traffic needs to flow in some different way to the way it's currently flowing, we need a little toolbox of spanners and wrenches we can use to try and shift traffic around. So, outbound traffic, we control our outbound traffic by changing how we process routes that we learn from other people. So we apply policy on the routes we learn from other people at the place where we learn them, because that's an easy place to do it. So we can have general policy. We can have a bunch of policies to do with BGP attributes that apply to peering links. So we prefer some particular peering places to other places. We prefer peering links over transit links. And we have specific policy as well, which might be short-term policy or it might be a long-term policy, which is to say things like, if we want to transit, we want to avoid a particular peering point for some reason, maybe because we have a congested interface there. So we'd like to try and depref the routes we learn over there. So we'll still use them if we have to. But if we have any other routes elsewhere in the network, then that's probably a better place to send the traffic. So here are some attributes that people commonly use to change their exit selection for particular routes. So local preference is a common one. Very commonly used to change the preference between customer and peer routes to avoid some nasty oscillations. MEDS, AS path. Different vendors have different BGP path selection algorithms. So depending on who your vendor is, you may be able to go down and find vendor-specific knobs or other knobs that basically allow you to control the outbound traffic in a way that makes sense. So the idea of making all these changes is to do small changes if you can. Small changes and then pause and wait and see what happens. Because there's a natural latency between things happening and people reacting to it. So changing something and then looking and saying, well, you know, the interface stats seem reasonable now. The pings are no longer taking 5 seconds to go across this OC12. Everything must be okay, I'll go home now. That's not really a good approach. The idea is to make very small changes and then basically repeat. So inbound traffic is a different sort of problem. Inbound traffic and controlling where your inbound traffic comes is all about influencing policy in other networks. So you're talking about influencing basically the outbound policy of your peers and transit providers, and also people in the world that have no connection to you whatsoever. So in general, this is a harder problem. So some providers give some degree of control to their customers and peers to allow those people to influence the way that exit selection is done in those foreign networks. So 1755, the WHOIS record there has an interesting selection of community strings you can set to influence the way routes are propagated through 1755 to other peers and customers. So lots of providers do this kind of thing. So you talk to your provider and people you directly talk to, you may find that there are particular community strings you can use to change the way that the routes that you advertise are treated by those other networks. And that can be a useful way of adjusting your inbound traffic. CIDR abuse. If you advertise a long prefix, the chances are the traffic will follow that as long as people receive that long prefix and don't filter it. So there are a bunch of networks around the place that do traffic engineering by advertising an overlapping set of prefixes. They might have a supernet, a /16 supernet, but for particular bits of traffic which they might prefer to advertise to receive over a different link, they'll advertise a /24, which is covered by that 16, down the other link. So they have a covering aggregate to make sure they don't lose any traffic. But they're kind of gambling on the fact that people are going to listen to the /24 and send traffic that way. And anybody who doesn't will send the traffic through the aggregate. So the reason this is an effective thing is because longest prefix wins is a very strong rule for trying to work out where to send packets in a forwarding table. No amount of BGP policy is going to override the fact that if you have a longer prefix route, that's the route that's going to get used. And the reason it's bad is because you end up putting all kinds of extra straight into the routing table, which is good for you, but the rest of the world has to endure it. So you're basically taking up space in all the routers of the world just for your own requirements, which is kind of rude. And it adds to sort of scaling problems and convergence problems and that kind of thing. AS path stuffing is another way to try and influence the exit policy that other people use in other networks. So basically, if I'm AS5, instead of just advertising the route straight to another person, I'll stuff it 5 times with AS5. So the path length now looks like it's been through 6 ASs. So this is a very common thing, but unfortunately AS path comes way down the list on the BGP tiebreaker list. So other people's local preference in MED is probably going to beat it. AS path pollution is a particularly nasty trick that I learned from someone in Australia. If I advertise a route over a particular circuit, and to suit my purposes, I really want to say, I want traffic to follow this link, but I never want traffic from, say, UUNet to come down this link. So what I'll do is I'll prepend 701 onto the advertisement before I send it, which means that 701 will never accept that route. So that's particularly nasty, because it makes people very confused when they look at the path and say, hang on a second, you're transiting 701 traffic. It can be very effective, but it can make things very confusing. And also, some people will actually put some filters on their inbound policy and say, we won't accept a route from anybody if it appears that they're transiting 701 routes, in which case your route just doesn't get accepted at all. So, I mean, basically, all these kinds of things, you have no direct control over the policy in other people's networks. So all these things are just things to try and edge a little bit more traffic one way, a little more traffic the other way. So you can try and sort of adjust the flow of traffic between different external links. So really, this is just a summary of the sort of slightly warning qualities of the previous slide. which is that some of these things are going to have unwelcome effects in other people's networks. They might be unwelcome simply because it makes operations staff confused. People might start saying, what the hell, I've just seen this weird thing on my routing table, and people might just waste time thinking about it. So even if the net effect on the other network is completely benign, you can still waste people's time, and wasting people's time is not a good thing. So basically, we all have to play nicely. That's the answer here. So I guess it's a balance. We have to try and do what's best for our customers because they're paying us money. But we don't really want to piss everybody else off in the world, because if we do, none of them will talk to us, and that kind of defeats the purpose. So we have some conceptual sort of goals that Josh and I were sort of talking about, and we came up with a couple of questions that we thought might be quite common. So the conceptual example, the first one, is basically who is chewing up my network resources. So we're concentrating now, for the purposes of our little experimentation, on outbound traffic. We're looking at where are we sending our traffic. And the reason we're looking at those sort of things is to try and control our outbound traffic. So we're looking at appropriate network expansion. Who should we peer with next? We might have particular peers that we need to maintain traffic ratios with. So it may be good, for example, not to send traffic to a particular peer if we can avoid it. So the interesting thing is to try and find out, of the traffic we are sending those people, if we're trying to reduce the amount of traffic we're sending, who are the main consumers of traffic beyond that AS? Maybe we can peer with those people directly. So another example is trying to spot from traffic flows when people are doing things that they shouldn't necessarily be doing. So this one here, theft over IP, is Josh's term. I don't know the responsibility for that one. The idea is to say, if we have a peer, this peer may have a problem due to a misconfiguration or perhaps some more nefarious purpose. They are sending traffic to us which corresponds to routes that we are not sending them. So they might be using us as a default. They might suddenly have a temporary problem that they can find they can relieve by sending traffic at us instead, because they know our connection to, say, another peer AS is better than theirs. And this is a thing, if you don't measure your network, you can never really tell this is going on until someone opens a trouble ticket. And if somebody may never open a trouble ticket because it may never cause anybody any problems, but even so, it's consuming your network resources by people who are not paying you. The Yahoo apparently are doing this kind of stuff. I don't know if you want to talk about this one.
Jeffrey Pavin over at Yahoo has done a lot of this stuff for a number of years now. He uses this appearance analysis that we've been talking about, expanding klufully. Expanding your network klufully, doing performance analysis, and even doing some manner of, instead of letting BGP select routes for me, I'm going to do active measurement, and I'm going to force it out different doors in my network, and I'm going to determine for myself who the best, and when I say for myself, I mean him for himself, what the best route is based on the performance characteristics, and I'm going to select routes based on that. So they do all sort of, custom macros for AS analysis, source and destination AS bandwidth details, where's my traffic going. I mean, all the stuff that we've been talking about, the folks at Yahoo have been doing for a while now. They do some stuff with chargeback billing. I don't know a whole lot about that. I'd have to ask Jeffrey about that. But DOS attack detection, performance analysis on their backbone, mapping traffic statistics onto their network and across their network, as well as outbound off their network. Yahoo pushes a lot of data, so traffic to the biggest aggregation points off of their network is a really, really good thing for them. And then on the next slide, there's a map that shows traffic that's syncing to one of their neighbor ASs and traffic that's transiting through their neighbor AS. And they actually view this in quasi-real time, so they can really see what's going on and who they're really shipping a lot of data through.
Okay, so the last few things we're going to talk about. It's an experience we had just recently over the past couple of weeks. Josh and I threw some configuration onto some routers in the MFN network and tried to have a look at answer some problems that we thought might be useful to answer. So you'll find these examples are not tremendously heavy on details, not to have too many specifics in them, because We have contracts with our peers that say that we're allowed to look at traffic data for the purposes of traffic engineering, as I think most people do, but they don't tend to cover sort of basically publishing that data and telling other people at a conference. So this is kind of sort of a little bit abstract, but the principles I think should be quite clear. So here's a network example that we tried to answer a question. So we peer with this particular large regional ISP in several places, and we're congested towards them. So we're not congested all day or anything, honest, but towards some of these people, over some of these peering links at certain times of the day, we get kind of busy. So what we're going to try and do is offload that. So who are the top people behind this large regional provider that we're talking to that we reach via them? So maybe we can peer with them directly. And not just the endpoints, not just the final endpoints of the ASs that are actually syncing the traffic, but for example, what aggregation points exist between them, what tier 2 providers or regional providers or whatever you want to call them behind this large ISP can we maybe talk to directly in order to offload the congested peering circuits. So we had a little look at the network. And although a lot of the network is sort of pure core edge along the lines that Josh described in his diagram, there are other areas where it isn't. There are other areas where it looks more like the ANS diagram. For one reason or another, expedience and availability of hardware, circuits get added where they need to get added. And people are not always thinking directly of measurement when they do it. So it's maybe not as convenient as we would like, but we can probably still do something. So in this example, all the peering routers are GSR 12,000s. All the peering circuits are OC12. And most, in the areas where we do have a hierarchical model, most of the links back to the core are OC48. So it's a GSR. We know we're doing sampling net flow anyway. There are OC48 circuits involved, some of which are quite busy. So maybe the sampling ratio is not going to be particularly close to 1-to-1 because we don't want to flood the network with measurement data. So the sampling thing is probably okay because we're looking at relative traffic volumes. We want to see for the to and through categories behind this large regional ISP, we want to be able to say, let's order these things by traffic to and traffic through and sort them and look at the people at the top of the list. So a couple of little things we found out. Turning on IP route cache flow sampled on an interface that didn't previously have it can cause the router to sort of pause for a second and contemplate its existence and wonder what it's doing here. And while it's doing that, the traffic kind of goes everywhere. So as we found out, turning that kind of thing on is good to do in advance or good to do in a maintenance window, and it's not particularly good to do at peak time. Inbound ACLs, as Josh mentioned, there's this contention for the feature set on inbound, for the inbound traffic management stuff on a line card. So we can't have ACLs running and expect to get net flow data as well. So a lot of interfaces, for one reason or another, will have some sort of ACL on them. Maybe peering links aren't necessarily the ones that do that. But in the parts of the network where we have multiple kinds of external links on a single router, so it's not purely peering, we might have ACLs out towards the customer, for example. And if we have an outbound ACL on a GSR is actually implemented as an inbound ACL on all other interfaces. So that effectively wipes out net flow from the entire router. So we have to turn off all the ACLs, and we have to talk to the people who put the ACLs on to find out whether it's appropriate to take them off. So these kind of things can take some time. And again, this is a little hurdle that can stop you just measuring in 5 minutes after you thought of a question. So we configure the export hosts. The routers start sending the data, and then the flood of data arrives, and we sit back and watch the disk nervously. So as I mentioned, what we're actually trying to get out of this data is a relative byte count through and to networks reached through the peering question. So if there's an AS one hop away, we want to know traffic that terminates in that AS, and traffic that goes through that AS, it doesn't actually terminate there. Because together that kind of gives an indication of how valuable that peer is in terms of peering or connecting directly. And again, absolute numbers don't matter. So this is some sample output from the tool that we used. It's not actually from this example; it's from a different example. But this is a tool that Ixia made called CFlow. But you could use all kinds of other tools to try and do it. In the past, I've done this by IX traffic. Sorry. In the past, I've done similar sorts of things by taking rather crude snapshots of the RIB, even just by expecting in a show IP BGP and trying to find out networks behind a peer. Storing a state and saying, well, I have an approximate table now of routes that I learned through that peer. So although it might not be sort of accurate up to the minute, it may be good enough to make a generalization. So we have some sort of idea of routes that are learned through a peer. Then what we do is try and match, as Josh mentioned, the destination networks from the flow data we received, match them up, and try and work out what AS paths correspond to different amounts of traffic. And if you're familiar with C-flow, then what we're basically doing is building a C-flow type matrix, but AS path is what we're trying to measure the traffic for. So we're taking instead of just an origin AS or a next top, IGP next top, or some other unuseful thing, we're taking AS path, which is a useful thing, and saying for every AS path we see, how much traffic do we send that way? So the reason for this slide here is it actually demonstrates it quite nicely. So you can see for a particular AS, the P indicates that we already have a session with them. And you can see we have packets per second through, we have bits per second through, and we have a sorted list, which is useful to look at. So we have another example now. We have somebody who comes towards us and says they want to peer. And that's good because we're good at peering, and we like doing peering with all kinds of people. But this particular person says, we don't really want to peer across an exchange that you're already at because we already consume a lot of your traffic. In fact, we say we consume 140 megs of your traffic at peak, so like a fast Ethernet connection over a peering exchange somewhere is probably a waste of time. So we want to pay a P&I. We want to do a private peering connection straight away. So they want us to allocate a port and do a direct interconnect with them. Now, it may be that we haven't really heard of ASR particularly much. Maybe they're kind of new. Maybe we don't have any sort of conceptual way of trying to work out whether that's a reasonable thing for them to say. Maybe they're just mistaken. So in any case, it would be nice to confirm the numbers and find out that we do really want to peer with them directly straight away and not waste our time with a public connection. So the answer we're trying to answer, the question we're trying to answer is how much traffic are we sending to this ASR? And we currently reach them through some other AST. And we peer with AST in a number of places. We have more complexities because some of the older peering exchanges still have some older routers on. And we have an overlap between this problem and the other problem. So we're going to end up getting flow data from one router that corresponds to both. Again, we have topology that is not edge core throughout the whole network. We want to get actual numbers out of this because we actually want to find an answer for how much traffic we're sending. And for various sort of recent localized reasons, we keep having to apply ACLs to various interfaces because we get large amounts of sort of unwelcome traffic directed at our routers from various places, which we have to kind of takes priority against measuring against some future peering things. So we're going to have holes in our data. And the chances are we're going to have holes in our data which don't correspond across the board because ACLs aren't applied everywhere simultaneously. So we might have one speaker that suddenly stops sending us net flow data for a while, and then another one that does it later, and we end up with this overlapping picture. So Josh mentioned this here. There are various tools that MRTG will measure the traffic from the interface counters. It will measure how much traffic we're sending across the interface. So to try and convert the relative numbers that we have, the sampled numbers that we have, to absolute numbers of bits per second, we can take a bunch of data which represents the throughput on an interface obtained through SNMP counters, or from counters obtained by SNMP, and we can divide that up in proportion to what traffic we think we're interested in. So there's probably some more to say about this. So the problem with the 7500 we kind of sidestepped because it turned out that was a public peering arrangement where the routes were so depreffed we weren't sending any traffic there anyway. So we could actually reduce the set of AST peerings for which we have to bother about by looking at the realities of how the routes were being depreffed through existing policy. So we could go through and say, of those original 6 peering places, in fact there's only 4 we have to worry about because the other ones just basically aren't used, the routes that are never normally selected. We did the trick with the MRTG thing. Well, actually, we have a tool called Duck, which does the same thing. So we could divide up and get absolute numbers for the throughput to AST that corresponded to traffic that was going through or to ASR. And the problem with the overlapping problem statement turned out to be not a problem at all. It's very trivial, basically, because none of the traffic that we were counting with the other provider obviously was had next top of AST. because it's all going to places in the other provider, which is not AST. So the fact that we had data from the same router answering both problems was just not an issue, because we could sort the data very easily and say data which corresponds to this question, which we'll use to make an answer, all has AST as the first next hop, which is a very simple way of splitting all traffic out that only corresponds to this problem. The problem with the ACLs that kept appearing and disappearing in various parts of the network was a little bit more annoying to try and spot. We could spot holes and find out where we didn't get flow data with an X top of AST from a router in a period of time, which is a fairly good indication that an ACL was put on. But it also could be something to do with the fact that there was some other routing policy going on. Maybe somebody changed the routing policy to a congested interface and deprepped a connection, which meant suddenly we stopped sending traffic that way. So the only real good way of tracking this down, which was kind of a crude way of doing it, is we have a tool called Rancid that probably many people are familiar with, which keeps track of our configurations in our routers and stores them in CDS. So we have a complete configuration history of sampled configurations which are polled every half hour. So with half-hour granularity, we can spot where an ACL has been applied to an interface, and therefore discount basically the entire pool of data for AST for answering this problem during that period, while we have any ACL on any of the interfaces we're talking about. So the problem with doing this, when you have a lot of ACLs being applied and pulled off, and when you have a half-hour granularity, is you end up with not necessarily an awful lot of periods of time where you can measure traffic. And also the periods where you can measure traffic might span a couple of weeks, but might correspond to different times of day, different times of week, and might not necessarily be representative of traffic flow during the entire period. So the ideal answer here is to try and beat on the vendors and make sure you can do ACLs and sample net flow at the same time. But absent that, the other thing is to try and do is just keep the ACLs off the router while you're doing the measurement. So this is our summary. The problems that we tried to track down during our experimentation just over the last couple of weeks were ad hoc questions. There were particular questions with very specific sort of problem ranges. And we tried to add configuration to the network to try and pull data out and answer those questions. So we found out that, we've already just completed the measurement stage. The next stage would be to actually go and make changes in the case of the first example, and to do that in an iterative manner. So we'll try and adjust the traffic flow in a slow, sort of controlled way, and then remeasure and see what changed. We didn't actually happen to measure from any Juniper routers because none of the questions concerned had any Juniper routers involved in them. And we didn't attempt to build a full-time general-purpose measurement infrastructure to answer these questions in a general way. That seems like a much harder question. But it might be sort of manageable for smaller networks, but when you have a few hundred routers involved, the collection infrastructure can be a sort of non-trivial sort of thing to design. And we also didn't talk about edge flows where the edge router doesn't have any sort of flow export. I mean, there are other boxes that apparently are available that you can insert in the physical transport path to a router, which will generate net flow records. So if, for example, if you have a router that you are unable or unwilling to generate net flow data from, there are vendors selling boxes where you can plug in into an OC12 or an OC3 or something like that, which will generate net flow data from the line. So in a kind of passive way. So I mean, there are solutions to that sort of thing, but we didn't have to try any of that because we were quite happy turning net flow on the routers. So that is it. Are there any questions?
Can you talk a little bit about the impact of sampling data all the time? What kind of traffic loads you see, what sort of hardware you need to back up large routers?
Well, the traffic that we recorded, the flow data that we recorded in these examples, we used basically a FreeBSD box at one point in the network with, I think, a 20 gig disk on it, which we just watched. And if we need to move things off and archive from somewhere else, we did that. But we certainly didn't need a huge sort of humongous data store in order to actually answer this question.
And then how much flow data was generated by capturing?
Do you happen to notice how much data?
But one thing we should mention is that we weren't recording the raw flows. We were manipulating the raw flows into aggregation tables, and then we were throwing away the raw flows, which you may or may not choose to do. So our requirements for disk usage were substantially less because of that. I think how many routers were there total? Like 12?
Something like that.
something like 12 routers, and all of them were doing 1 in 100 samples.
Yeah.
On some number, between 3 and 8 high-speed interfaces, OC12, OC48. And I want to guess that per router, we were collecting something like 12 meg a day, 20 meg a day, something like that. I mean,
it sounds reasonable.
It wasn't an order of magnitude off from that. So as long as you were keeping the aggregation cables and not the raw flows, which are voluminous and can chew up disk really fast, the disk requirement was not out of hand.
We were not exporting V5 directly to it.
We were exporting V5 directly, but we were not keeping historical records of these raw flows.
We were basically using the data to populate that AS path matrix. And once the matrix had been populated, we threw the data away. So we could do that because we're answering specific questions. Even sort of semi-specific questions like AS path matrices across the network, which still allow you to answer general questions. They don't contain all the data that you could be able to go back and say, well, what actually happened last Tuesday? Because now that we know this, in fact, there was some sort of spike here which caused a problem. So let's go investigate it. So we've discarded that data by that point. So with the way we measured for this example, we couldn't answer that question. Can we comment on the dollar implications of doing measurement for traffic engineering? I think the answer is that we didn't talk directly about dollars, and Josh will probably have something to say about this as well. We didn't talk directly about dollars, apart from references to Josh and snake oil. But basically the idea is that if you have a problem in your network that you need to solve, then a very sort of tempting way to solve it, if you have unlimited money, is just to go out and upgrade everything. So if you think one circuit to someone is congested, then you can just go and buy a bigger circuit or buy another circuit. And you can keep doing that. The idea of doing traffic engineering is you don't necessarily have to do that. That's not the only way to answer the question. So if we have a particularly congested peering circuit towards this particular person, or transit circuit, then there may be alternatives to upgrading it straight away. We may be able to go out and gather other peering sessions across public exchanges where we already are, and basically lower the cost of delivering our traffic without congestion, and that way save spending the money.
Yeah, I mean, VJ's big bit is that in order to do traffic engineering, you require traffic. Sans traffic, you can do very little traffic engineering or very little worthwhile traffic engineering. And over the last number of years, I mean, a lot of the major carriers and even a lot of the smaller carriers have found that they have just oodles and oodles of internal capacity, right? I mean, and when you have an internal capacity problem, you throw another link at it, and therefore you don't. And even though they've spent, 100,000 hours designing internal traffic engineering systems, there's enough existing internal network fiber, if nothing else, that allows people to really throw bandwidth at the problem. Inter-domain, that doesn't tend to be the case. If I'm provider X and Joe's provider Y, well, I'm sure we both have plenty of fiber, but not between each other. So there's costs with external relationships. There's costs with ports, there's costs with administrative costs, there's costs with having interdomain links to be able to get the biggest bang for your buck by figuring out whom am I going to dedicate an expensive router port to, because who am I going to go peer with? You may be paying those people because you're buying transit. You may be paying those people because your traffic ratios are such that you're paying a settlement fee. You might be lucky enough to just be a standard peer, and that's great, but there's still costs associated with that. If you are paying settlement fees to some upstream provider, you're paying settlement fees because you qualify as a peer, but your traffic ratios don't quite meet their criteria. Using this to make your traffic ratios fit into their criteria can obviate costs for you. And then, the other example is just clearly, using this stuff to go find the consumers of your bandwidth and consumers of your resources. Those are people that use the stuff that you provide, and those are sales opportunities. And I don't want to stand up here, with my sales hat on and tell you guys to go off and sell to everyone, because it's not really, what the NANOG gig's about. But there are really good reasons to do this stuff to drive revenue and to save costs.
What about BGP accounting?
BGP accounting is pretty useful, except you need a priori knowledge of what you're looking for. And so for the second example, you could use that. The problem with that is that if you don't know exactly what you want, or if you think that what you want may change based on what you learn, or if you need to know more than 6 buckets or 8 buckets, I can't remember the number, it's useful in the same space, but it's pretty limited. You have to know exactly what you need to know ahead of time, and you need to measure it in the right places, although you do with here too. But I think of this as a much more flexible approach to answering a much broader scale of questions. But like DCU and the bucket of counters for BGP do have some application in the same space. Again, you know, memory usage on the box, some of the same issues in deploying it, especially on the Cisco's with the iOS issue. But yeah, I think it's on the list. It's somewhere further down the list too. So if you're doing sample net flow and DCU or the Cisco equivalent,
That's right. It's further down.
yeah. So yeah, you can use that in some places. Other questions? One more. You can do it. No?
140 meg number in your presentation.
Say again?
Well, how much time is this 140 meg number you referred?
140 meg number. Which 140?
140 meg number.
You're doing that all across.
Yeah, that's what it says you are consuming the resources because of 140 meg number. Like, what is the intensity of traffic actually? Per second, per month?
Sorry.
On the graph?
Yeah, no.
This is the NANOG.
What, pairing with AST, that one?
Yeah.
Oh, that was their claim of how much traffic they exchanged.
Per what time?
No, I think they're talking about a peak demand. So if we're going to avoid congestion.
140 megabits.
Per second at peak load.
140 megabits
So,
per second.
right.
Yeah.
Don't find anything.
Actually, the analysis is still ongoing on that one. So we haven't quite decided yet.
Yeah.
We have some answers, but we haven't checked them enough to decide whether they're true or not.
Having worked in that environment, there's some architectural constraints, but there's a harder problem.
Anything else? Thanks for sitting through it.